Assalamu alaikum girls. I am Shamsunisa from Royal Degree College Chemistry Department. As we are dealing with Inorganic Chemistry Chapter 1 Chemical Bonding, today we'll study about hybridization and types of hybridization. Hybridization. It is the concept of intermixing of the orbitals of an atom having nearly the same energy to give exactly equivalent orbitals with same energy, identical shapes and symmetrical orientations in space. The new equivalent orbitals formed are known as the hybrid orbitals. These orbitals have properties entirely different from the properties of the original orbitals from which they have been obtained. So the hybridization involves two steps. First one is excitation and the second step is reorientation. First of all, we'll see about excitation. First step. The carbon atom in the ground state has the configuration 1s2, 2s2, 2px1, 2py1, 2pz0. It absorbs some energy when an electron from 2s orbital is excited to the vacant 2pz orbital. Thus, the configuration in the excited state is 1s2, 2s1, 2px1, 2py1, 2pz1. Now we'll see about the second step, that is reorientation. The orbitals containing 4 unpaired electrons rearrange themselves into an altogether new order. It gives rise to the hybrid orbitals which are identical among themselves. Now we'll talk about types of hybridization. Hybridization involved in case of carbon is of 3 different types, which is depending upon the number of Hopfield atomic orbitals taking part in it. First one is sp3 hybridization, which is tetrahedral. Second one is sp2 hybridization, trigonal hybridization. Third one is sp hybridization, that is linear hybridization. And the other types of hybridizations are sp3d, sp3d2 and sp3d3 hybridization. Now we'll see about sp3 hybridization, that is tetrahedral hybridization. When 1s orbital and 2p orbitals of excited carbon get intermixed to form 4 hybrid orbitals. These orbitals are known as sp3 hybrid orbitals. This phenomenon is called sp3 hybridization. sp3 hybridization involving one spherical non-directional 2s orbital and 3 dumbbell-shaped p orbitals, that is directional, which are oriented along 3 axes at right angle to each other, gives 4 equivalent hybrid orbitals. They are directed at an angle of 109 degree 28 minutes with respect to one another. So these orbitals arrange themselves in the form of a regular tetrahedron. Therefore, the hybridization is also known as tetrahedral hybridization. Each sp3 hybrid orbital has 25% s character and 75% p character. Hybrid orbitals consist of 2 lobes, one of which is quite large while the other is small. Here you can see the example of methane and ethane. It is the example of methane, where you can see how many sp3 hybrid orbitals are there? 4 sp3 hybrid orbitals, isn't it? So in between the 2 sp3 hybrid orbitals, angle will be, the bond angle will be how much? 109 degree 28 minutes. Now we'll see about the formation of methane, in which sp3 hybridization is involved. In methane, the 4 Hopfield orbitals of carbon, before taking part in bond formation, mix up their energies and redistribute equally to give 4 new and equivalent sp3 hybrid orbitals, which are directed at an angle of 109 degree 28 minutes with respect to one another. The 4 sp3 hybrid orbitals overlap with one s orbital of 4 hydrogen atoms. Here you can see the figure, to form 4 s single bond sp3 sigma bond. The 4 bonds in CH4 are directed towards the four corners of a regular tetrahedron. Bond length of each carbon-hydrogen bond is 1.09 degree angstrom, and in between hydrogen, carbon and hydrogen, the bond angle which is forming is 109 degree 28 minute. Next, we'll see how the formation of ammonia molecule takes place. In ammonia, nitrogen and hydrogen is there, isn't it? Central atom is nitrogen, which is showing the atomic number 7. Electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz1. And hydrogen, as it is showing atomic number 1, its electronic configuration is 1s1. So 1 2s and 3 2p orbitals of nitrogen of nearly same energy intermix to give 4 sp3 hybrid orbitals. One of the 4 hybrid orbitals contains a lone pair of electron. Here you can see which orbital in the nitrogen is showing the lone pair of electron, that is 2s orbital, and half filled 1s orbital of 3 hydrogen atoms overlap with half filled sp3 hybrid orbitals, these 3 sp3 hybrid orbitals, to form 3 s single bond sp3 sigma bonds, except one with lone pair of electron. So the expected geometry of ammonia is tetrahedral, but due to lone pair bond pair repulsion is greater than bond pair repulsion, there is some distortion in the shape of the molecule. The bond angle is slightly less than 109 degree 28 minute. So the bond angle in case of ammonia is 107 degree, and molecule assumes pyramidal structure. Here you can see the structure. Next is sp2 hybridization, which is also named as trigonal hybridization. When 2s orbital and 2p orbitals, that is 2px, 2py of excited carbon atom get intermixed to form 3 hybrid orbitals, then these orbitals are known as sp2 hybrid orbitals. This phenomenon is called sp2 hybridization. These hybrid orbitals are directed at an angle of 120 degree with respect to one another. As the 3 hybrid orbitals are directed towards the 3 corners of a equilateral triangle, therefore it is also known as trigonal hybridization. So here each sp2 hybrid orbital, here you can see how many sp2 hybrid orbitals are there? 3. So each sp2 hybrid orbitals has 33% s character and 67% p character. One of the p orbital remains unhybridized, which is not taking part in the hybridization. Which orbital? That one is 2pz. It lies in a plane perpendicular to the plane of the hybrid orbitals. Here you can see the figure. And in between the 2 sp2 hybrid orbitals, bond angle will be how much? 120 degree. Now we'll see the formation of ethylene or ethene. In CH2 double bond CH2. What is CH2 double bond CH2? That is nothing but ethylene or ethene. Each carbon atom of the carbon-carbon double bond undergoes sp2 hybridization, leaving 2pz orbital unhybridized. The 3 sp2 hybrid orbitals lie in one plane. These are used in making 3 sigma bonds, resulting in a planar structure. Each carbon atom lies at the center of a triangle. The 2 hydrogen atoms and the other carbon atoms are directed towards its 3 corners. Unhybridized p orbital of the 2 carbons lie in a plane perpendicular to the plane of the hybrid orbitals. So here the 2 partially filled unhybridized p orbitals of 2 carbons form a weak pi bond. How? By sidewise overlap. The pi bond consists of 2 equal electron clouds distributed above and below the plane of the line joining the 2 carbon nuclei. Thus, in ethylene, here you can see the structure. In ethylene, all the 6 atoms, what are those 6 atoms? 2 carbon and 4 hydrogen, forming sigma bonds lie in one plane. Okay, and the pi bond is in a plane perpendicular to the plane of the 6 atoms. So here in case of ethene, how many sigma bonds are formed? 5 sigma bonds and 1 pi bond. So the among the 5 sigma bonds, the 4 sigma bonds are formed in between the carbon and hydrogen. Okay, and 1 sigma bond it is formed in between both the carbon. Okay, and 1 pi bond is forming in between the 2 carbon. Now we'll see about the features of pi bond. Pi bond is weaker than the carbon-carbon sigma bond. Why? Due to lesser overlapping of electron clouds. The bond energy of carbon-carbon double bond is 615 kilojoules per mole. The bond length of the carbon-carbon double bond of ethylene 134 picometer is less than the bond length of carbon-carbon single bond, that is 154 picometer in case of alkanes. The shortening of bond length is due to 2 reasons. Okay, so here the shortening of bond length is what? Why? Due to the 2 reasons. The first reason is additional sidewise overlapping of p orbitals brings the atom closer. Next is the carbon-carbon bond in case of ethylene and other alkenes is formed by the overlap of sp2 hybrid orbitals of carbon instead of sp3 hybrid orbitals as in ethane and other alkanes. And sp2 hybrid orbital has more s character than sp3 hybrid orbital. As s orbitals are smaller in size in comparison to the p orbital, the effective size of the hybrid orbital decreases with increase in s character. Thus, the bond length also decreases with increase in s character of the hybrid orbitals. So, the carbon-hydrogen bond length in case of alkenes is also slightly shorter than carbon-hydrogen bond length in case of alkanes. The presence of a weak pi bond in ethene makes it highly reactive in nature. So it is regarded as an unsaturated molecule. The overlap of 2 unhybridized p orbitals is maximum when they are parallel to each other. This is possible only if all the 4 groups along with the 2 carbon atoms lie in one plane. Now we'll see about sp hybridization, which is also named as linear or diagonal hybridization. When one 2s orbital and one p orbital, that is 2px of excited carbon atom, get intermixed to give 2 hybrid orbitals, then these hybrid orbitals are known as sp hybrid orbitals. And this phenomenon is called sp hybridization. These hybrid orbitals are directed at an angle of 180 degree with respect to each other. Here you can see in the figure. Therefore, sp hybridization is also called linear or diagonal hybridization. Each sp hybrid orbital has 50% s character and 50% p character. Now we'll see about the formation of acetylene or ethyne. In acetylene, both the carbon atoms are sp hybridized. One of the sp hybrid orbitals overlap with sp hybrid orbital of the other carbon atom to form a sp single bond sp sigma bond. The remaining two sp hybrid orbitals of 2 carbon atoms overlap with the s orbital of 2 hydrogen atoms to form 2 sigma bonds. The unhybridized 2py and 2pz orbitals of 2 carbon atoms overlap laterally to form 2 pi bonds. The sum of one sp single bond as sigma bond and two p dash p pi bonds is called the triple bond. Bond energy of the carbon-carbon triple bond is 812 kilojoules per mole. Bond energy of carbon-carbon double bond is 615 kilojoules per mole. The bond energy of carbon-carbon single bond is 348 kilojoules per mole. So the bond length is in the order carbon-carbon triple bond length is less than carbon-carbon double bond. Carbon-carbon double bond length is less than that of carbon-carbon single bond. So like that, the carbon-carbon triple bond length, it is 120 picometer, which is less than 120 picometer, which is less than carbon-carbon double bond length, that is 134 picometer. Okay. So the carbon-carbon double bond length is less than carbon-carbon single bond length. How much? 154 picometer. Like that, if we are calculating in degree angstrom, carbon-carbon triple bond length is 1.20 degree angstrom, which is less than carbon-carbon double bond length, that is 1.34 degree angstrom. It is less than carbon-carbon single bond length, that is 1.54 degree angstrom. The carbon-hydrogen bond length in acetylene is 106 picometer. How much it is? 106 picometer. Here you can see the figure, that is the diagram of acetylene. In between the two carbon atoms, triple bond is there. The one triple bond is one of the bond, that is sigma bond. Rest of the two bonds are pi bonds. And in between carbon and hydrogen, single bond is there, which is nothing but sigma bond. Now we'll talk about sp3 dehybridization. Example here we are taking, that is phosphorus pentachloride. Here you can see the figure. In this compound, ground state electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. And the excited state electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s1, 3px1, 3py1, 3pz1 and 3d1. It undergoes sp3 dehybridization. One s orbital, three p orbitals and one d orbital involved in hybridization. So it is sp3 dehybridization to form PCl5 molecule with 5 sigma sp3d single bond p bonds. Each sp3d hybrid orbital has 20% s nature and 60% p nature and 20% d nature. The molecule assumes trigonal bipyramidal shape. Bond angle in one plane will be 120 degree. Here you can see in the figure. And 90 degree bond angle, which is perpendicular to the plane. Now we'll talk about sp3d2 hybridization. Example here is SF6, sulfur hexafluoride. Here you can see the figure. Sulfur is present at the center. And how many fluorine atoms? 6 fluorine atoms. It is present around the sulfur. Electronic configuration of sulfur in the ground state is 1s2, 2s2, 2p6, 3s2, 3p4. Excited state electronic configuration is 1s2, 3s2, 2p6, 3s1, 3px1, 3py1, 3pz1, 3dxy1, 3dyz1. So here in this 1s orbital, 3p orbitals and 2d orbitals are involved in the hybridization. So it undergoes sp3d2 hybridization. The molecule assumes octahedral shape with bond angle 90 degree. Okay. In sulfur hexafluoride, there will be 6 sigma sp3d2 single bond p bonds. Now we'll talk about sp3d3 hybridization. Example is iodine heptafluoride. Central atom is iodine here. Atomic number of iodine is 53. Ground state electronic configuration of iodine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d10, 5px1, 5py1, 5pz1, 5dxy1, 5dyz1, and 5dzx1. So here you can see one s orbital and 3p orbitals and 3d orbitals are involved in hybridization. So 7 atomic orbitals, what are those? 1s, 3p and 3d involved in hybridization. So it hybridizes to form 7 sp3d3 hybrid orbitals. These are singly filled. These hybrid orbitals overlap with singly filled 2pz atomic orbitals of 7 fluorine atoms to form 7 I single bond F sigma bonds. Iodine heptafluoride molecule assumes pentagonal bipyramidal shape. Here you can see. And the bond angle is 72 degree and 90 degree. Thank you for listening my lecture.